I actually went ahead and filled out, well, partially filled out the tables for the two graphs that we're going to be generating on page 1. But I do want to let you know in advance that the log, or the logarithm, is our second of the two functions we're spotlighting in this chapter, and it happens to be the inverse of an exponential function. What we did last time was generate a table of values to graph the function 2 to the power of x. And I have a table filled out, not in as much detail as what we did on Monday, but the point still stands. And what I'd like to do is plot these points in this coordinate plane that I have as best as we can. Okay, I know plotting things like 0.125 and 0.25 require some approximating, but make sure you have these values in that first table. And once you have them, go ahead and get them plotted. And I'll do the same right now. All right. I'm going to start at 0, 1 and connect the points to the right of it. And you may recall one end of this exponential graph skyrockets to outer space, and then the left end of it approaches the x-axis without ever crossing or touching it. And that would be the graph of 2 to the x. Okay. To find the table of values for the inverse function, this was mentioned in the section 6.2 video lessons. Does anybody recall how we can form the graph of an inverse function based on a table of values? There's something special that we do with x and y. So what we're going to do is we're going to switch all of these. And what I mean by that is the x values will turn into the y values and vice versa. So with regard to the inverse functions graph, the first point on it is going to be 0.125, comma, -3. The next point will be 0.25, comma, -2, and so on and so forth. Okay, so if you have a set of points from the graph of a one-to-one function, which 2 to the x is, it passes the horizontal line test, then all you need to do is switch the points, or switch the x and y coordinate, and you'll get points on the inverse function. Now to plot 0.125, -3, I'm going to start at the origin and go over just by a skosh to the right, and then go down to the tick mark of -3. And that point is really, really close to the y-axis, but it's not touching or crossing it. And then 0.25, I'm going to go a little further than that to the right, and then down by -2. And then 0.5, -1, so I'll go halfway between 0 and 1, and then down by 1 unit. And then we get to some easy points to plot. 1, 0, 4, 2, 8, 3. And let me show you how to connect these. Let's start at the point 1, 0, and to the right, it's just going to slowly hook through these points and steadily increase its way to positive infinity. To the left of 1, 0, we get another end, but this end will approach the y-axis without ever crossing or touching it. And that would be the graph of the inverse function. Now let's talk about this end right here. Because that end is approaching the y-axis, something that we can assume about it is that it's neither going to touch or cross the y-axis, but this end does get closer and closer to it, what does that mean about the y-axis? What could we qualify that as? Vertical asymptote, exactly. So I'm going to draw a vertical asymptote going along the y-axis, and that would have an equation x equals 0. Now with the function 2 to the x, the domain was all real numbers. The range was 0 to infinity. The horizontal asymptote was y equals 0, and it contained the point 1 comma 0. Let's look at the specs of the inverse function. You may recall that when we switch the x and y values to get from the regular function to the inverse function, the domain and range switch. So what you're going to see happening is that the range of the original function becomes the domain of the inverse, and the domain of the original function becomes the range of the inverse. So the domain for this orange graph is going to be 0 to infinity. The range is going to be all real numbers. And hopefully that makes sense, because the bottom end of the graph goes down to negative infinity, whereas the right end of the graph goes up to positive infinity, but a heck of a lot slower than this end on the graph of 2 to the x. What also happens when you form the inverse function this way is that the asymptotes become perpendicular to each other. Case in point, we don't have a horizontal asymptote for the inverse function, but we have a vertical asymptote, and instead of y equals 0, it would be x equals 0, since it's a vertical line now. And then instead of the graph going through one, oops, I'm sorry, I gaffed on that. So for 2 to the x, the point that it goes through is 0, comma 1. It's on the inverse function that the graph goes through the point 1, comma 0. Okay, so without any transformations, we know that exponentials go through 0, 1, and that point's coordinates get switched to be a point on the inverse function, and wouldn't you know it, we have a point that's going through 1, comma 0. And this is really the nature of inverse functions, right? Everything just kind of gets flipped around. And so that's the graph of the inverse of 2 to the x. In just a little bit, we'll give it a name. But for right now, I'd like you folks to take a couple minutes to form the points on the inverse function for the graph of 1/2 to the x, and then graph both these functions using this coordinate plane. Okay, so I'll check in with you in just a few minutes to see how we did, and then we'll go from there. Alright, I'm going to try to catch up with you guys. So again, we're going to switch the x and y values of the original function to get points that are on the inverse. All right, I'm going to plot the original function now. All right, as we'd expect from an exponential function whose base is less than 1, the left end of the graph goes up to positive infinity, whereas the right end approaches the x-axis. Now I'll plot the points for the inverse function for -2, 2, -1, 1, 0, 0.51, then 0.25, 2. I'm going to start us at 1, 0, and I'll connect the points that are underneath the x-axis. We're going to curve our way through them and just indicate that this end of the graph goes down to -infinity, but at a very slow rate. And to the left of 1, 0, we're going to have another end which gets close to the top part of the y-axis, but never crosses or touches it. Okay, so our first graph is 1/2 to the power of x, and then our second graph would be the inverse of that function. Now, because this end approaches the y-axis without ever crossing or touching it, we have another vertical asymptote going along the y-axis. And that would have the equation x = 0. This end of the graph is going down to -infinity. And we could do a same side-by-side analysis of the domain, range, asymptote, and so on and so forth. But you may recall from Monday that all of the features of a graph with a base less than 1, other than its orientation, are all the same. So it'll kind of be duplicative. So I'll forego it for this graph. But is this what you guys came up with? Excellent. Well, here comes the official definition of a logarithm. And long story short, a logarithm allows us to isolate exponents. Specifically, if there's ever something in the exponent that we want out of there, like back down on the ground, that's what I like to say, then we use a logarithm to help us out with that. So for instance, if we started out with f of x equals a to the x, and we wanted to find the inverse of this function algebraically, we first rewrite f of x as y, and then what we do is we switch the position of x and y, so this becomes x equals a to the power of y. And then the next thing that we would do is try to isolate the variable y. But there's no regular algebra that could help us do that. And this was a problem for a long time back in the history of math, is how do you isolate this variable if it's in the exponent? Well, it took some ingenuity, and I believe it was a Scottish mathematician that laid out the foundation for this all. To get this out of the exponent, he devised a way of rewriting the equation. And rewriting the equation is basically how we do this, how we get the variable out of the exponent. And what we use to rewrite the equation is what's called a logarithm of base a. So it says here, if x equals a to the power of y, then the logarithm of base a is given by let's write log. Logs have a base, just like exponentials. And in this case, the base of the log will be the original base of the exponential. We can plug things into logs, and there's going to be a space for us in order to do so. So back in line with the word log, I'm going to write parentheses and then the variable x. And then I'm going to say that this is equal to y. So this is basically a rewrite of x equals a to the y, only it's using a logarithm. Okay? So a couple of side notes here, and then we'll do the fancy Winnie the Pooh. There's stuff I want to fill out in there. So this number a, that's a subscript between log and parentheses x, is known as the base of the log. And it says here it's always positive and never equals 1. And the reason for that is because that's exactly how we define the base of the exponential. So the subscript on the log is the log's base. Whatever's inside the log's parentheses, in this case the variable x, that's referred to as the argument. All right, and I want no arguing from you on that. Just messing. And we'll see that there are some restrictions on the argument later on. The variable y is the exponent of the original exponential expression. So I'm going to say OG exponent. And what I mean by that is the exponent from our exponential version of the equation. Now what's helpful about logs is they allow us to go between exponential form to logarithmic form. Exponential form is what we started out with, x equals a to the y. Logarithmic form is what we just defined, log base a of x equals y. So in the case of the function 2 to the x, if we tried finding the inverse of this function algebraically, just using our standard algebra operations, we'd be left off with x equals 2 to the y. And the issue is that y is in the exponent. But now that we have a logarithm, we could write this as y equals log base 2, since that's the base of our exponential expression, of x. And I'm going to make Winnie the Pooh just a little bit more fancy. All right, any questions so far? So we're going to get to some equations, but before that, I want to show you how you can rewrite, an exponential form to log form and vice versa, because that's going to be a helpful skill with equations. And we'll get practice with using what's called a log loop, which is what I like to teach for this skill. We'll get some practice with converting, talk about two of the most common types of logarithms, or most popular types, and then we'll get into equations, and we're going to round off this section with transformations. So this first part in this table, I want to show you how you can use what's called a log loop to go from log to exponential form. So let's say that this was already written down, log base a of x equals y, and we wanted to go to the exponential format of this equation. Now to set this up, I'm going to scaffold it with some boxes. This box will go the base. This box will go the exponent. I'm going to write the equal sign, and then this box will go the argument. Now going back to log base of x equals y, we're going to start with a, and I'm going to loop around the right-hand side and finish off inside of the log. And there's three variables that we come across when we do this log loop. The first is the base a. That's what I'm going to put in this first box, is a. The next variable that we come across is the variable y, and that's what I'm going to put in the second box. The last variable that we come across is the argument x, and that's what's going to go in this box. Okay, so we start at a, that goes in the first box. We encounter y, that goes in the second box, and then we finish off in the argument, which goes in the third box. Does that make sense? Well, let's say that we were first presented in exponential format, a to the y equals x. Let's write log for log. Every log has a base, so I'm going to put a box for the base. A log is going to have an argument, so I'm going to put a box in there. And then a log is always equal to something, which I'll put a box for that. Let's start at the base a of the exponential expression. We'll wrap ourselves around x and finish off in the exponent y. The first of these letters that we encountered was the base a, so that's what's going to be the base of our log. The second variable we encounter is x, and that's what's going to be the argument of the log. And then the last variable that we encounter is the variable y, which is what's going to go in our last box. Okay, so we start at the base. That's the base of our log. We wrap around the item on the right-hand side. In this case, it's x. That's going to be the argument. And then we finish off in the exponent, and that's what the log is going to equal. So logarithms are nothing more than just a different way of writing an exponent. Okay, so that's how we go from exponential to log form. Let's get some practice with this. So it says here, change the statement to an equivalent statement involving either an exponential or log expression. Now, if you look at examples 1 through 3, they're all presented to us in log format. So the only way we can go is to exponential format. Let me scaffold this with some boxes, and you don't have to write these boxes out if you don't want to. It's just without any lined paper, it's a little more difficult to tell what's in the exponent and what's not. So I just thought about this last night, and we'll see how it goes. So we're going to do a log loop, and we're going to start at the base 3. Okay, we're going to wrap ourselves around 4 and finish off at 81. The first number that we used or came across was the number 3. So that's going to go in our first box. We wrapped ourselves around the number 4, so that's the second number we encountered, so that's going to go in our second box. And then we finished off in the argument, which doesn't have parentheses around it, and that's pretty typical. That's the way the author writes it, but if you want to put parentheses in there, you're welcome to. But anyway, 81 is where we finished off at, which that's what's going to go in our third box. So without the boxes, this says 3 to the 4th is equal to 81. And that would be the exponential format. All right, everything making sense so far? All right, can I have you guys try problems 2 and 3? All right, so I'll go over these. For problem 2, start at 16, wrap around 3/4, and finish off at 8. I think I'll need a longer box for the exponent. Okay, so the first number we use is 16. That's going to be the base of our exponential expression. We wrap around 3/4 next, so that's going to be the exponent. And then we finished off at 8, which is going to be the number on the right-hand side. So without the boxes, this is 16 to the 3/4 is equal to 8. And then for number 3, we start at 10, wrap around 0, and finish off at 1. So 10 is going to be the base of our exponential expression, 0 will be the exponent, and then 1 is what 10 to the 0 is going to equal. Which, if you think about it, all of these statements that we've come up with as our answers are legitimate statements, right? So for instance, 10 to the 0, yeah, definitely equal to 1. So it's just kind of a bougie way of writing exponents out. That's what logs are. We're going to do log loops in the other direction now, because for 4, 5, and 6, all expressions are given as exponential expressions. So the only way that we could go from here is to rewrite it in log format. For number 4, let's write log. Every log has a base, so I'll set a box up for that. I'll set a box up for the argument. And then on the right-hand side will be our exponent from the exponential expression. So for a log loop, with exponential format, we start at the base of the exponential, which is 5, wrap around the right-hand side, and finish off in the exponent. So the base of the log is 5. What's going to go inside the argument, folks? 625. And the only other number we haven't used yet is 4, so that's going to go over here. So without the boxes, log base 5 of 625 is equal to 4. Okay. We'll do number 5 together, and then I'll give you a shot with number 6. So we're going to start at E, wrap around 9, and finish off at X. So what's the base of our log? E, yep. The argument? 9er, yep. And what's going to be on the right-hand side? X. So check it out. If this were an equation situation that they asked us to solve, we'd obviously be solving for X. And by converting it to log format, we actually have X back down on the ground. We would only need to figure out what this equals, which we'll see how to approximate that in just a minute. But yep, that would be the log format of number 5. Go ahead and give number 6 a try. I'll check in with you in just a moment. right, let's see how we did. 1.2, wrap around m, finish off at 3. This should be log base 1.2 of m equals 3. Sound like a winner to you folks? Winner, winner, spaghetti dinner. All right. So any questions so far? Okay, let's move on. So there were 2 logs in that set of examples that represent 2 of the most popular logs. They're so popular that they actually get buttons on the graphing calculator, as we'll see in just a second. I'm going to call these special logarithms, not only because of the base, but also because of the notation that they get. The first of these special logarithms is a common logarithm. And what makes it a common logarithm is the fact that the base is 10. So if we saw something like log base 10 of x, the more usual way to write this out is without the 10. Okay, so if you see log and there's no base written, you can assume that the base is 10. The other type of logarithm that's special is a natural logarithm. And this would be the case where the base is equal to e. Okay, remember e is that 2.718-ish number. So one way of writing this log out is log base e of x. But the more common way to write it is ln parentheses x. So if ever you see ln, that stands for natural logarithm, and it's kind of backwards. I think because it has like some Latin ties to it, I think it goes like logarithm natural or something, and I can't help but sound like my Uncle Harry from Tennessee, logarithm natural. But anyway, that will be the notation indicating that the base of the log is e. So I mentioned that these logs get buttons on the graphing calculator, and for these upcoming examples, I'm going to show you how you can punch these in. All right, so it says use a calculator to evaluate each expression, round to 3 decimal places. Our first log that we're going to evaluate says log, and you'll notice that the base isn't written. So this would be a base 10 log, or in other words, a common logarithm. And let's go to our graphing calculators, and I'll show you where to access this button at. If you look to the left of 7, you should have a button with log on it. Go ahead and press that, and it kind of sets up the argument for you, only it's asking, hey, what the heck do you want in here? Okay, so let's type in 25. And as soon as we have our arguments typed in, I strongly recommend closing off the set of parentheses. Okay, let's go ahead and press enter. And to 3 decimal places, what do you guys think about 1.398? Is that what you're getting to? All right. So let me go back to the notes. We'll approximate that. Okay, so 1.398. It's always helpful to know what your answer means. And I'll go ahead and explain exactly that. I'll say meaning. So remember, this log has a base 10, and we have the option to rewrite this in exponential format, which I'd like to see what that does. That'd be 10 to the power of 1.398 equals 25. Not equals, but should be close to 25 since we had to approximate our answer. And if we go to our graphing calculators and type that in, 10 to the power of 1.398, we have some evidence that it truly is our answer to this problem. But notice it's not exactly 25, and that's because we rounded 1.398. I actually should be over 6 feet tall, but there were some rounding errors in utero. So, there's that. Okay. The next one that we want to type in is the natural log, or logarithm natural, of 3 over 2 divided by 0.4. I included this one because there's some common mistakes that happen when typing in the logarithms, and I'd like to address that. The LN button is to the left of your 4 key, right, directly underneath the log button. Let's press LN, and we'll type in 3 over 2. And let's say that we forgot to close the parentheses, and we hit the division key again to type in 0.04. So this is almost like what's typed out in the notes, except it's missing the other parenthesis. Your calculator will still grind through, the calculation, but this answer of 3.624 is actually incorrect. And the reason for it is because without closing the argument's parentheses, your calculator thinks that all of these numbers are inside of the natural log. Let's contrast this with the natural log of 3 over 2, closing off the parentheses, which is how it's typed out in the notes, divided by 0.04. We get an entirely different number. And this is actually the proper answer, 10.137. So again, without closing off the argument, in the first version, your calculator thinks that all 3 of those numbers are in the argument. But now, by closing off the argument of 3 over 2, your calculator understands that 3 over 2 is the only number in there. Okay? So parentheses are definitely really key with these logs. Yeah, at any rate, we got an answer of approximately 10.137. Any questions, comments, concerns, winning lotto numbers, anything like that, folks? All right. So we had a first encounter of exponential equations on Monday. We're going to have a first encounter of logarithmic equations today. And I'm going to show you 2 techniques which help us isolate the variable x, which you can expect x to be inside the argument of a log in some way, shape, or form. And when we have a log with the variable x inside the argument, that's what qualifies it as a logarithmic equation. Now, not every log equation can be solved this way. We will look at more advanced techniques later on in Chapter 6. But the equations that we'll be presented with today are kind of like special cases where we can get by solving one type just by rewriting, and the other type by using a very similar one-to-one property like exponentials had. So it says here, sometimes the best way to solve a log equation is to rewrite the equation in exponential format. So let's revisit that. Let's say that we had log base a, and inside the argument was an algebraic expression with x. And on the right-hand side is just some constant number. We know at this point that we could convert this to exponential format by taking the base a, writing it to the power of n in this case, and setting it equal to m. Now, one thing that isn't completely spelled out here is that there's nothing in front of the log, which is kind of critical. Okay, if there are any numbers in front or behind the log, you have to get rid of them before you convert to exponential format. All right, so let's get to work on these examples. In part A, we have log base 3 of 3x minus 1 equaling 2. There's nothing in front of the log, and there's nothing behind it. So this puts us in a position to rewrite the log using a log loop, which is about the only way that you can start to free up x out of the argument. So let's start at 3. We'll raise it to the power of 2, and then we'll set it equal to 3x minus 1. All right, and I'll use boxes here just so we know where everything goes. Okay, so we started at 3, the base, so that's going to be the base for our exponential. We're going to raise it to a power of 2 because that's the second number, and then we're going to set it equal to the argument, which is 3x minus 1. In other words, 3 squared equals 3x minus 1, and by rewriting it, you get rid of the log notation, and you end up in familiar territory. Why don't you guys go ahead and solve for x and report the answer in the chat. You got it. So 9 equals 3x minus 1. Add the 1 over to get 10 equals 3x. And divide each side by 3 to get x equals 10 thirds. Very good. All right, can anybody see an issue right out of the gate with problem B? The 4, exactly. Yeah, this time we do have something in front of the log. Now, when it's written in front of the log like that, it's being multiplied. So to get rid of this 4, we could divide each side by 4. That gets us log of 2x is equal to 1/4. By the way, what's the base of this log since it's not written out? You got it. So remember, when the log base isn't written, you can assume that the base is 10. Now, x is inside the argument, and the only way to get it out of there right now is to rewrite it in exponential format. So let's start at 10. We'll wrap around 1/4 and end off at 2x. So 10 to the power of 1 over 4 is equal to 2x. And just like that, we're one step away from isolating x. What should we do to each side, folks? How about divide by 2? So x would equal 10 to the power of 1/4 all over 2. All right, any questions so far? Oh, by the way, all of our answers for x at this point are exact answers. My math lab might ask you for both the exact and the approximate answers. I think we're okay with typing in 10 over 3, but to type something in like 10 to the 1/4 all over 2, We'll type in 10, and then just use the caret key for 1/4. And since that exponent is a fraction, just to make it crystal clear, maybe use parentheses around 1/4. And then divide by 2. So an approximate answer would be 0.889. All right, is that good? Okay, so the first version of this answer is what we consider exact, and the second version would be an approximate. Moving on to part C. Okay, so let's check. Is there anything in front of this natural log? Nope. Nothing behind it either. By the way, what is the base of the natural log? E, you got it. So I'm going to write E there, and I'll set up our boxes. We'll start at E, wrap around 5, and finish off at 2x plus 1. So our base of the exponential is E. Its power is going to be 5, and then it's going to equal the expression 2x plus 1. That's e to the 5th equals 2x plus 1. Now e to the 5th is something that we could punch into our calculators, but I say we hold off until we get x by itself before we do that. To start solving for x, let's subtract 1 from each side. We'll write the left-hand side as e to the 5th minus 1 after we do that. And then it's 2 times x, so we're going to divide each side by 2. Now when you divide the left-hand side, make sure it goes underneath all of the expression e to the 5th minus 1. And so x would equal, in an exact format, e to the 5th minus 1 all over 2. Now to get an approximate answer, I strongly suggest using a set of parentheses around the numerator, since it has 2 terms. Let's go ahead and do that. Okay, so parentheses. The E button, you have to press second key, and then natural log. Let's type in 5, and we'll get back down on the ground. Big minus sign 1, and close off those parentheses, and divide by 2. All right, so do I have confirmation on 73.707? All right. Okay, let's take a 5-minute break. When you guys come back, I'll show you one more technique for solving, and then we'll wrap class up with transformations. See you soon. All right, folks, welcome back. Let's keep this log a-rolling by discussing the one-to-one property of logarithms next. Okay, so we just saw one technique which helps us isolate the variable inside the argument of a log. Basically get rid of the log by rewriting the equation. Another technique is to use the one-to-one property, which says this. If your equation is written in the format log base a of something equals log base a of another something, represented by m and n, then you can just set these arguments equal to each other. So in words, we could say that equal logs implies equal arguments. All right. This to me, I think I'm going to start calling it the headphone method, because if we put a circle around m and n, it kind of looks like a pair of headphones, or maybe a music note. But anyhow, this is kind of the logarithm analogous of the fishing lure method that we were talking about on Monday. Now, there are some strict requirements here, okay? The bases of the logs do have to be equal to each other, and there has to be a log on both sides, okay? For example, in problem 1, we have log equals log, and the two bases are equal to each other. So we are allowed to use the one-to-one property here. Now, if this were log base 3 and the right-hand side was log base 5, then we'd have to do something else. All right, but the fact that we have log base 5 equals log base 5 means that we can use our headphone method here and set the arguments equal to each other. Okay, so we could pretty much abandon the logs here and write 5x plus 3 equals x plus 11. Subtracting x and 3 simultaneously would give us 4x equals 8, in which case our answer should be x equals 2. Go ahead and try out problem 2. We'll go over it, and then we'll look at the final stage of chapter 6.4. Right, any volunteers? That's what the answer might be? All right. So we have natural log equals natural log. So we're free and clear to use our headphone method. The original Beats by Dre. I'm going to call these Beats by C. 6x minus 5 equals 2x plus 7. It's going to give us 4x equals 12, leading to x equals 3. You guys got it. Okay, in section 6, we'll look at some more advanced techniques. All right, this is just a little primer, and these are really kind of like special case log equations. All right, we'll get to some of the more advanced ones later on. All right, this is just to wet the palate a little bit. So we're going to finish the notes off today with transformations, and I'm going to give a similar breakdown of what we can expect log function graphs to do prior to any transformations, and then I'll give you some tips and tricks for how to do the transformations. So like I said, a lot of what we're doing today is kind of a repeat of what we did for exponential functions, right? After all, they are inverses of each other, so we probably should give equal treatment, right? So So we're going to finish things off with looking at general properties of the graph of log base a of x. And again, in the words of Megan Trainor, it really is all about that base with the logs as well as the exponentials. There are two ways the base a can go. It could be greater than 1 or it can be less than 1. Now if the base a is greater than 1, your log graph will go through the point 1, 0. And it's also going to go through the point a, 1, which if the base is greater than 1, a, 1 is going to sit a little bit elevated and to the right of 1, 0. Now as we saw with the inverse of 2 to the x, and the inverse is given as log base 2 of x, if we start at 1, 0 and go through this point a, 1, it's going to slowly increase its way to positive infinity, whereas to the left of the x-intercept, we're going to have an end approaching the y-axis without crossing or touching it. There is a vertical asymptote along the y-axis. And additionally, you may recall the 1-unit gap from exponential functions. There's a similar 1-unit gap with logs, but this time it's in the horizontal direction. All right. Now the domain and range of the log switch the domain and range of the exponential. The domain of the log is going to be from parentheses 0 to infinity. All right, and if you look at our blue graph here, that's entirely to the right of the vertical asymptote. And so all the positive x values are being used to make it. None of the negative x values are. And then we do have one end going up to infinity and the other end going down to negative infinity, which makes the range all real numbers. And this is a reversal of what we had for exponential functions. If you trace this graph from left to right, it's always increasing. And it contains the point 1, 0. And I think I'm going to add here a, 1. And then the vertical asymptote is x equals 0, which is the equation for the y-axis. If the base is less than 1, the graph will still go through 1, 0, but this time a, 1 is going to sit higher but to the left of the point 1, 0. And as we saw with the inverse of 1/2 to the x, which was a log, to the right of 1, 0, we're going to have one end slowly decreasing to negative infinity, whereas to the left of 1, 0, we're going to have an end approaching the y-axis without crossing or touching it. Okay, so that qualifies the y-axis as another vertical asymptote. And this graph also has a 1-unit gap. Now, other than the fact that the graph decreases from left to right, everything else is the same as when the base is greater than 1. So the domain is all real numbers. I'm sorry, 0 to infinity. The range is all real numbers. Contains the 2 points 1, 0 and a, 1. And then the vertical asymptote is x equals 0, which is the y-axis. All right, any questions? So we're going to apply some transformations to these types of log function graphs. And let me go ahead and present the order in which you do it, as well as some tips on how to find some of the additional info, such as domain range, asymptote, and so on and so forth. Let's say that we had f of x equals minus log base a, and in its argument, x minus h, and at the end and outside of the argument, plus k. The very first thing that you do is identify the base. Now keep in mind the base will either be greater than 1 or less than 1. And so depending on the value of a and how it compares to 1, you might have a graph like in the first box, or you might start out with a graph like in the second box. Okay, so always identify your base graph. What you do from there is you look for any negatives that are in front of the log. Now they won't always be there, but if they are, that's the second thing that you look for. And because it's on the exterior, if you will, that would prompt an x-axis reflection. There may be addition or subtraction to x inside of the argument. And because this is happening inside a grouping symbol, the parentheses, this would represent a third transformation, which is the horizontal shift. And then you still have to think backwards with horizontal shifts with logs. Last but not least, you might have addition or subtraction by a number at the tail end. And what do you think that might do to our graph? Yep, up or down. So that's going to be a vertical shift. So remember, with vertical shift, you can think normal. Now here's some additional tips. For the domain, you're going to want to solve x minus h is greater than 0. Okay, so once we solve for x with this, we get an idea of the legitimate x values that can be plugged in the log. All right, and from a numeric standpoint, x minus h being set greater than 0 means that we can only plug positive numbers inside the log, which I can get into in a later session that we have. As for the range pretty much by default, that's how these functions are constructed, is always going to be all real numbers. The vertical asymptote can be found by solving the equation x minus h equals 0. I'm going to say solve this. And then we'll use our graph to figure out where the x-intercept 1, 0 moves to. All right, I'm not going to give any formulas for that. I'm just going to say use graph. Okay, so these are tips on how you can find, that additional information, much like we were doing back in section 3. So let's go ahead and start applying this. So it says here, sketch each function using transformations, identify domain, range, asymptote, and the new location of 1, 0, if any. The very first thing that we want to do is identify the base, which the base is 2. That's a value of a that's greater than 1. So this is going to start out as a log graph that increases from left to right. And 2 points that would be on the base graph here would be 1, 0 and 2, 1. And I'm going to connect these points, the dash graph, this end going to positive infinity, and this end going down to negative infinity. That's going to be our first graph. There's nothing in front of this log in terms of negative signs, so there's no x-axis reflection that we have to worry about. But there is something going on inside the argument. What do you think this does to our graph? Yep, left by 1. So I'm going to take these 2 points, shift them left by 1. The vertical asymptote shifts left by 1 as well, but I'm going to leave that off until our final graph, just so that it doesn't look too messy in this coordinate plane. I'll try to keep this the same shape as possible from graph 1. And then it looks like we're subtracting at the tail end of this function. So what does that mean? Down 3. Yep. So I'll use graph 2's points, shift them down by 3 units. And keep in mind, there's that 1 unit gap between the vertical asymptote and the new location of the x-intercept, which is right here. Okay, that's where our x-intercept moved to. There's a 1 unit gap, and our vertical asymptote is going to be to the left. And it appears as though we'll go through x equals -1. So what I'll do next is simply connect our 2 points, much in the same way as we did in graphs 1 and 2, to the left of our new x-intercept, which is now a y-intercept, by the way. We'll approach the vertical asymptote without crossing or touching it. Kind of liven these points. There we go. And that's our final graph. So let's see how to work the domain. For the domain, we're going to set the inside x plus 1 greater than 0. And we'll solve this inequality by subtracting 1 from each side. And it would say that x is greater than -1, which in interval notation is parentheses -1 comma infinity. All right, and that can be verified using our graph, because if you look at our orange, our final graph, that's completely to the right of x equals -1. Okay, it's not 0 to infinity though, because we have one end of the graph getting close to the VA. As for the range, it's kind of a memorized fact. That's going to be all real numbers. For the vertical asymptote, we're going to set x plus 1 equal to 0. And solving for x, we get x equals -1. Which, if you look at our graph, that's exactly where the vertical asymptote crosses the x-axis. And then does anybody want to tell me the final location of 1, 0? 0, -3. Okay, so I'm going to highlight all of our specs here: domain, range, vertical asymptote, and new location of 1, 0. And I'm going to request that you work out problem 2. All right, so I'll give you a few minutes to work out problem 2. We'll go over it, and then we'll do a couple more. All right, let's see how we did. The base is greater than 1 again. It'll go through the point 1, comma 0, and a comma 1, which in this case would be 3 comma 1. No minus sign in front of the log, but we are subtracting 2 inside the argument. So think opposite here. It's going to be right by 2. I'll take each of these points, move them to the right by 2. The vertical asymptote moves to the right by 2 as well, but like the last problem, I'm going to leave it off until the end. And then we have plus 1 trailing this function, and that's going to be a vertical shift up by 1 unit. And keep in mind the 1 unit gap. Okay, that's going to help us identify our vertical asymptote, where it goes. Actually, let me liven these points a little bit. And let's see, so I'll connect these 2 points much like we did with graphs 1 and 2. And the left end is going to get close to the VA without crossing or touching it. And that should be our final graph. That what you guys came up with? All right. Now for our domain, we're going to set x minus 2 greater than 0, which gives us x is greater than 2, and in interval notation that would be 2 comma infinity, which as you can see our blue graph is entirely to the right of the VA, which you can tell is crossing at x equals 2. The range, memorized fact here, all real numbers. VA would be x equals 2, and the original x-intercept of 1 comma 0 moves to 3 comma 1. Okay, so there's the new x-intercept right there, and that's at 3 comma 1. All right, how's this stuff going for you so far, folks? All right, well, let's move on. We'll do number 3 together, and then I'll have you guys finish class off with number 4. So number 3 involves the natural log function. The base here is e, which is certainly greater than 1. And 2 points that would be on this graph, let me label them off to the side, would be 1 comma 0 and e comma 1. All right, so keep in mind e is approximately 2.71828, so let's leave it at 2.7. Let's plot 1 comma 0 and 2.7-ish comma 1. So we get another increasing graph. This time we do have a minus sign in front of the natural log. And what that's going to do is it's going to give us an x-axis reflection. So 1 comma 0 is on the x-axis, so when you reflect that, it doesn't really move anywhere. But e comma 1 is now going to move down to have a y-coordinate of -1. And so I'll connect these 2 points. Okay, now this end is going down to -infinity, and the left end is going up towards the positive part of the y-axis. And then inside the argument, we're adding 5, so we're going to have to move our graph left by 5. So let's take those 2 orange points. We'll move them to the left by 5 units. I'll start with 1, 0. And that e -1, all right, we'll kind of have to eyeball this. 1, 2, 3, 4, about right there. And then keep in mind that 1 unit gap for the VA. Okay, our VA looks like it's going to cross the x-axis at -5. And I'll connect our two blue points so that one end goes down to -infinity and the other end gets close to the gets close to the VA without crossing or touching it. Does that make sense? Now for the domain, what you'd find is that it's -5, infinity. The range, memorize fact, all real numbers. The vertical asymptote, if you set x plus 5 equal to 0, you get x equals -5. And then the point 1, 0 relocates to -4, 0. That's where our new x-intercept is at, -4, 0. Okay, any questions about number 3? All right, then let us, as in the produce department, get some time to work on problem 4. I'll check in with you folks in a few minutes. We'll go over it, and that'll be it for today. Okay, I'm going to try to catch up with you folks. This time the base is less than 1. So it will go through the point 1, 0, but also 1/2, 1. So 1, 0, and then 1/2, 1 will force the left end of the graph to go along the positive part of the y-axis, and the right end of the graph to go down to -infinity. Based on +4 inside the argument, we'll have to go left 4. And then after that, down 3. Maybe we can do both those at the same time, just to save on some writing. I'll start with 1, 0. Okay, that's going to go left by 4, and then down by 3. So the x-intercept ends up in this location, which is at -3, -3. And then we'll move the point 1/2, 1 left by 4. So go to the left by 4 whole units, and then down by 3. Now there's that 1 unit gap between the new location of the x-intercept and the vertical asymptote. And then we'll just go ahead and form the shape of the graph, much like that in drawing number 1. That would be our final graph. All right, as for domain, we'll set x plus 4 greater than 0, giving us x is greater than -4. So it's going to be -4, comma, infinity. Range is all real numbers. Vertical asymptote, it's going to be x equals -4. And you can probably spot a pattern between the equation for the VA and the domain. They should incorporate the same 2 numbers. And that's actually the case with all of our domain and VA answers. And then 1, 0 relocates to -3, -3.